Alright, in this lesson we're going to look at solving inequalities instead of equations. And before we get into the algebra, the analytical manipulations, we're going to see if we can interpret inequalities graphically. Using the graphs is going to support the algebra, and it's going to prevent us from making the kinds of mistakes that happen when students solve without thinking graphically. So, just looking at our first example, we have an inequality which says x minus 5 has to be less than or equal to 2. We should understand what the question is being asked, and the question is being asked is, which values of x make this a true statement instead of a lie? So, any number that I choose for x that makes the number on the left-hand side smaller than 2 is a solution. Any number that makes the number on the left bigger than 2 will not be a solution to the inequality. So that's the essential question that we're trying to address. Now what we can do is take the first left-hand side and express that as a function in terms of y. So every x that I choose, which is represented on the horizontal number line, is going to produce the value for the left-hand side of the inequality. For example, when x equals 0, the graph indicates that the y value, or the left-hand side, will be negative 5. You can see when you put in 0 for x in this, you get 0 minus 5, which is negative 5. So that's what we have here in this black line, is all the representations of all the corresponding values for the left-hand side, depending on what x is. Now the algebra behind solving this equation is really simple, but again the focus here is going to be on the geometry itself. So on the right-hand side is y equals 2. This is all the places where y equals 2, horizontal line. And then I observe that my graph indicates when x equals 7, these left and right hand sides will be equal. 7 minus 5 is equal to 2. So we can see right there that x equals 7 is the point of equality. Now what we're trying to do is to find inequality. We want the values of the left hand line to be lower than the values of the horizontal line. And on the graph we can see right there, when x is smaller than 7, we produce values for the left hand side that are below 2. So less than equates to below in these 2D graphs. So this enables me then to express in interval form my solution set. Its x is any number. Remember, this epsilon is Greek letter E. It represents the phrase is an element of, or often called a member of. So x is a member of any number from negative infinity to up to 7, including the number 7, because of the less than or equal to. This is the old school version of the same statement. And to verify, I just pick any number that's less than 7. Since 0 is less than 7, it should be true in this equation. 0 minus 5 is less than 2, which is true. Negative 5 is in fact less than 2. So we pass. Over here, quickly now, we can see the left-hand side represents a line. We can write as a function y equals 3x minus 4. The right-hand side is y equals 5. We can see the point of equality is at x equals 3. And we can verify that because 3 times 3 is 9. 9 minus 4 is 5. So when x is 3, both parts of the graph intersect at the same place for x equals 5. Now, again, what I'm looking for is values where the line is less than 5. When x is smaller than 3, it produces values for the left-hand side that will always be below 5. Therefore, I write my solution set as x is any number from negative infinity to 3, including 3 again because of less than or equal to. The verification, any value of x that's less than 3 should make this true, which it does, so I will count all of these as correct. Now in this we have greater than instead of less than or equal to, but the method is the same. 2/3 x minus 4 representing the left-hand side values, negative 8 representing the right-hand side values, negative 6 representing the point of equality. This time, though, we do not want x to be negative 6 because we do not want the left and right sides to be equal. When x is negative 6, the left and right-hand sides will both be negative 8. The graph shows that as I increase from negative 6, that is, as my x values go above negative 6, the y values for the left-hand side will increase above negative 8. Thus, my solutions now are going to be any number from negative 6, not including negative 6, up to infinity. Once again, in simple verification, This last one is where things get a little interesting, and I'll explain as we go, but the same procedure applies. We identify the equations of each line, and then we can identify the point of equality, and once we know the point of equality, we just have to use the graph to determine whether we're going to be above or below 1.5. In this case, we want the values of the left-hand side to exceed -2, so we want all the stuff to the left of 1 1/2. So there's our solution set, and verified. But here's where things get a little interesting. Just looking at the algebra briefly, we'll do more with the algebra later, but right now I just want to point out that if I wanted to solve this inequality, all I have to do is treat it like an equation. I just add 5 to both sides, and I get my solution. We knew that x was less than or equal to 7, but just from looking at the graph, I can verify just by doing simple algebra, x is certainly less than or equal to 7. Now here, in the bottom right, we found that x has to be less than 1 1/2, so when we're in this direction, we'll have a line left-hand side above -2. Now if I apply the same principles of algebra that I did up here, that is, first I'm going to subtract 1 from both sides, so that gives us -2 becoming -3. Then I'm going to divide both sides by -2, giving me x greater than 1 1/2. We can clearly see from looking at the graph that if x was greater than 1 1/2, that we would not be greater than -2, we would be below -2. Now if I look at this equation from a different approach, I'm going to add 2x to both sides, then I'm going to add 2 to both sides, and then I'm going to divide by 2. That creates the correct solution, the correct solution of x less than 1 1/2. That's what we discovered from the graph earlier. So here we see some ambiguity. That is, the algebra for inequalities is virtually the same as the algebra for equalities, with one exception. Here, when I solve this way and divide by +2, I get the correct solution, but when I solve this way and divide by -2, I get the incorrect solution. That creates the rule that says whenever you divide inequalities by negative numbers, you reverse the inequality. So we're going to skip this method. I contend that if we just solve the equation, y equals 2x, -2x plus 1 equals -2, and we solve that equation, -2x equals -3, x equals 3/2. Once we find the point of equality, then we can take a very simple glance at our graph and show that we should be x is less than 1 1/2. So the procedure for solving inequalities is, rather than worrying about trying to remember when you switch the sign and when you don't switch the sign, I say just solve the equation instead of the inequality, and very quickly graph and see whether we should be above or below. It gives us a deeper level of understanding and a higher certainty of getting correct solutions. So, just one last quick example. The process that I'm using for graphical interpretation, it works the same, even if the left and right hand sides are both lines that are not horizontal. So here, for example, y equals 4 minus x is a line whose slope is -1, y-intercept of +4, and here's the line y equals 4x minus 1, y-intercept of -1, slope of 4. Find equality at x equals 1. And then we can see that if we go larger than 1, that the left-hand line, that is the one that's really steep, should be above, this says above, 4 minus x. So that happens for all x's larger than 1. Thanks for watching. Have a great day.